Hey, I feel like doing some calculus problems. Let's go. Gonna be using my power rule. Nice little shortcut for taking derivatives. All right, let's go. Let's get cranking. Number one, directions say find dy dx. Well, I'm cool with that. Dy dx is the same as f prime of x, which is the same as y prime. That's the three ways that we write the derivative symbolically. All right, so number one, if y is equal to 4x to the 7th, then dy dx is equal to 28x to the 6th. Now, for those of you who like to write the least amount of stuff as possible, I just want to point out here that this is, in fact, the least amount of stuff possible. You need to have a complete sentence, a complete mathematical sentence with this. Here's your verb here. Dy dx is this. You can't just write that. Sorry. It's not about showing your work. It's about having a complete thought and expressing that complete thought to other human beings. So that's just the way it is. All right, moving on. Dy dx is equal to 24x to the 7th plus 2. This is easy, right? Just kick that exponent down. It multiplies to something out in front if there is something, whatever coefficient, and then you drop the exponent by 1. That's the power rule. Oh, here we go. Watch out for this. Dy dx is equal to pi cubed. You know what pi to the third power is? Me neither, but it's probably about 30, I guess. It's a number, right? Pi to the third is just a number. It's a constant. And you know what the derivative of that is? It's 0. So if you put 3 pi squared, ooh, you fell in that trap. A pi is not a variable. So the power rule is for if you have let's say if y is equal to x to the n power, then dy dx is equal to n x to the n minus 1. Right? This has to be an x. This is not for like whatever you want here. It's x to a number. That's the only situation where this works. Lots of situations where we have that though, right? All right, so what about 7? What should we do with this? If there's a constant on the outside, you can just leave that there. Constant is good. 7x to the 6th plus 2. And I don't know, you can distribute that if you want, but there's not really any benefit to doing that here, so I'm not going to. So 9, they switched up the directions. Oh, they're asking us to find f prime now. Can we handle that? Of course, it's the same thing. So negative 3x to the, be careful here, negative 3 minus 1 is negative 4, not negative 2. And then the 1 over x to the 7th, the power rule only works for if it's x to the whatever. So you need to rewrite, or at least reimagine, the 1 over x to the 7th. That's x to the negative 7. Oh, it's this. That is not the same. It's not 1 over 7x to the 6th. Power rule does not say that you can do that. There are other rules for dealing with fractions, rational expressions. We don't know them yet. We're going to learn them soon, real soon, next section. 11, f prime of x is equal to negative 8 times negative 3. It's 24x to the subtract 1 from the exponent is negative 9. And then 2 times the square root of x, that's 2x to the 1/2. So the 1/2 kicks out to the front, multiplies by the 2, right? So that just turns into a 1x. And then the new exponent was x to the 1/2, subtracting 1 from that. That's now x to the negative 1/2. Right? So maybe now you're starting to think to yourself, oh, right, so that's why it's so important for us to know about rational exponents and negative exponents, because it's got to be written like this. All right. Now the power rule doesn't say anything about composite functions. So here, like this, f of x is equal to 3x squared plus 1 squared. It doesn't say that I can just bump this out to the front and then drop it by 1 if there's more inside here than just an x. There's a rule for dealing with composite functions that we will learn in, I think it's section 3.6. I get 3.5 and 3.6 mixed up sometimes. It's called the chain rule. Actually, I got the pacing guide right in front of me. Does it say it on here? It does. Yeah, it's 3.6. So we'll learn how to do that, but for now, to get this into like power rule form, I got to FOIL this out. So that's 9x to the 4th plus 6x squared plus 1, and now I can find the derivative of that. Now it's in good shape for me. So that's 36x to the 3rd plus 12x. It's not really optional. You have to do that until there is another rule for dealing with that, but we don't know yet. So got to do it that way. And then 15 is kind of a generic third-degree polynomial, so it'd be 3ax squared plus 2bx plus c, and then d is just a constant, so that goes bye-bye. And 17, find y prime of 1. Okay, so I'm going to find y prime, and then I'm going to plug 1 in. So y prime of x, which is the same as just writing y prime. That's like f prime of x. F and y are interchangeable in that way. Is 10x minus 3. So y prime of 1 is 7. How about that? Let's see. I think I can keep using this paper. Let's move. How about here? What am I? Oh, I'm not on 17. I did that. 19. Find dx dt. What? Oh, wait a minute. This is like physics, right? They're throwing this in here for students of physics. So dx dt, that's like a position versus time graph, right? That's cool. So that means if usually we find dy dx, that's when it's usually like y equals and there's stuff happening with x's. So dx dt, we would expect something exactly like what we see in 19, x equals and then stuff happening to t's. So there's nothing different about the process here. dx dt is equal to 2t minus 1. Number 21. Find, okay, so notation thing, if this freaked you out here, I can't remember if I did this in the, if I went over this in the notes or not. I have a bad feeling I didn't. You might not have seen this notation before. So this just means dy dx at x equals 1. It's the same exact thing as saying what's f prime of 1. Why would you write it this way when you could just write it this way? Well, if you have the dy dx notation at x equals 1, then that's how we do that. We don't write, I don't know why exactly we don't, but we don't do this. We don't do dy dx of 1. That notation is just not done. So this is how we write it. So it just means find the derivative and plug in 1. All right, so for 21, what's my dy dx? dy dx is, the 1 goes away, then derivative of x is 1 plus 2x plus 3x cubed plus 4x to the, oh, I messed something up, didn't I? 3x squared, trying to go too fast. Not that it would matter, because I'm just plugging in 1, but try to support all things that are true in the world. A lot of things that are floating around out there that are not true these days. Most unfortunate. Science is really good at figuring things out, you know, and like things like the Earth is warming up and people are partially responsible for that. That should be in the realm of things that are like politics is just very frustrating and sad, because it's not a political question, it's a science question. All right, so that's that. In number 23, we got that situation where you got to do a little bit of algebra to simplify first. So, before I take my derivative, got to do some algebra. But look at what happens here. Isn't that cute? That after all that, we just end up with a difference of 2 squares. So the foiling here, it's not nearly as bad as what one might imagine at the start. All right, so there's that. So then we can find dy dx easily. The 1 goes away, so that's negative 8x to the 7. And dy dx at x equals 1 is negative 8. All right, as it was 23. Let's see if I can fit 25 and 27 in here. 25. Ooh, different directions. All right, let's see what's going on here. So approximate f prime of 1 by considering the difference quotient f of 1 plus h minus f of 1 all over h. You should recognize that as part of the definition for the derivative. So the limit as h approaches 0, f prime of 1. This is how you find f prime of 1 for any function. You plug 1 in for x, and then you do the definition of the derivative, right? For values of h near 0, and then find the exact value by differentiating. All right, so I guess they want us to just find for values of h near 0. I don't know. I mean, how many values are we going to do, like of near 0? I'm not too keen on doing a lot of messing around, but I guess we could do 1. If you just do this, that's like a secant line, right? If you don't actually do the limit thing. So values of h near 0. So how about like 0.01? Let's try that. I think I'm going to have to bust out a calculator to do that. Maybe if I do 0.1, maybe I can do that by hand. Let's see. Not feeling too good about that with the x cubed, though. Let's just do for h equals 0.01, and we'll break down and use a calculator because this is just an annoying problem. So that means I need to find f of 1.01 minus f of 1 over 0.01. And make no mistake, this is the slope formula, right? That's y minus y over x minus x. The difference, the h is the difference between those two x values. You know what 1.01 minus 1 is? It's that. So this is just finding the slope of a secant line where we have slid that point real close to f of 1, real close to x equals 1. All right, but now I got to plug 1.1 in for x. So that's 1.01 cubed minus 3 times 1.01. Probably could have done that in my head, but whatever. Plus 1. And then I'm going to subtract whatever I get when I just plug 1 in. So that should be easy. 1 minus 3 plus 1, that's negative 1. So minus negative 1. That's the top of that. And if I just hit the divided by this now, I'd make a mistake because I don't have the whole thing. I should have put another set of parentheses around that whole thing. So I'm just going to do, and that's what I get there, and then I need to divide by 0.01. And I get 0? What? Oh, I think I'm in some weird mode here. Yes. Let's get out of that. There we go. That was for weird rounding stuff. So 3.01 I got there, and then they want me to find it again just by actually finding the derivative straight up. So let's see if we can do that. We got f prime of x is equal to 3x squared minus 3. When I plug in 1 into that, I get 0. So let's see, what did I do wrong? Let me try this again. My calculator might have, well, I guess it's my fault really. So there's this, and then I need to divide that by 0.01. Oh yeah, there it is, sorry. So I'm not sure why exactly that happened, but the exact value is 0. So f prime of 1 is 0. What's that problem about? It's just trying to remind us about what we're really doing here, and that the behind the scenes there are limits happening, and just like you saw in your notes, the power rule and all these other rules depend on going through first and finding out what happens when you use the limit definition. Okay, so 27, use a graphing utility to estimate the value of f prime of 1 by zooming in on the graph. Okay, I think we can do that. And then do the exact. So I've got f of x is equal to x squared plus 1 over x. Now, you got to watch out for this. This happens sometimes. We're just dividing by a monomial here. What that means is I can divide through each one of these just by x and simplify this. So x squared over x is just x, and 1 over x is x to the negative 1. Now this is in power rule. It's power rule friendly. This is not. So the mistake that a lot of algebra students make is they try to do some kind of simplifying like this when there's like some plus or minus stuff going on the bottom of the fraction, and that you can't do unless you can factor and get the same factor to show up on the top and the bottom. But if you just have a monomial on the bottom, you can just divide through by that, divide all the pieces through. Right? It's like having a common denominator and breaking it up into the two things like before it got put together, right? Oh, a common denominator, I could put that together like this. But it turns out breaking it up like this and then rewriting it here is what we need to do. Okay, so here's a graphing utility, my calculator. Oh dear, look, that's the last thing I was doing, some polar stuff. Polar calculus is pretty fun. That's way down the road. It's like the last thing we're going to do. So let's get out of that mode. Function. I don't want to be in a plus bi mode either. Let's get out of that. All right, now let's see. We got x plus x to the negative 1. And I never hit graph before I look at what my window is. This looks like a trig kind of window. Not really interested in that. We're going to, which would be a good window for us? We want to estimate the value of f prime of 1. So I don't really need a big window. So I think just maybe guessing here, how about like a -2 kind of window? Let's see what that looks like. Not good. So let's try, how about I go back to my standard window. I'll do zoom standard. That goes to your -10 to 10. Let's try that. Okay, so if I want to do around x equals 1, so do you know how to do a zoom box? That's kind of a fun thing. So if I do a zoom box right here, number 1, you get to, it's kind of like the snipping tool on your computer. You hit enter and then move the cursor around and drag it over. So now whatever's in my little box there, it's going to blow that up. Okay, cool. So now the thing is, if I wanted to just kind of look at the graph here and like move around, I might not try. It looks a lot like the slope's 0 right here, doesn't it? It looks like that's a minimum of it. So I guess we could just go with that. But if you were gonna, if it had a non-zero slope and you were gonna try to guess and say, oh, I think this has a slope of whatever, just by looking at it, like 1/2 or 1/3, you'd really want the window to be square, meaning that you'd want this distance between tick marks here to be the same as this distance. So you were looking at something that was scaled the same, or like they call that squared up. So if I wanted to do that, I'm just going to show you here. I don't think we need it here because it looks like it's 0, but you can go to zoom 5 is z square. It will take whatever window you have and square it up for you. So it turns out like this was a little steeper than it looked on our graph. So there's, move my cursor around. There's pretty close to 1. It looks like the slope is 0, so that's what I'm going with. So looks like f prime of 1 is 0 by inspecting the graph. Now let's see if that's actually true. So what is f prime of x? It's 1, and then here this would be the -1 kicks out to the front, and then we drop that exponent. So when we plug 1 in for this, 1 minus 1 to the -2 is still 1, so it is indeed 0. All right, some calculator stuff there for you. What do we have left? 37. Oh, I didn't even need to do 25 and 27. That is hilarious. Well, I hope you skipped those. If you didn't, I hope you learned something from that. I don't really know if I learned anything from that. That seems like a mistake that I'm just as likely to make again. I think I probably didn't learn anything from my mistake there. That's a bad example for you. Okay, so 37, the directions say find, what does that mean? That just means the second derivative. Oh, do I want to explain to you, now you might be wondering like why are those 2's weirdly staggered like that? Sure, I'll explain it real quick. So there's a version of this dy dx thing. Let's say you have, for example, y equals x squared, and you want to take the derivative of that. Well, you'd be finding dy dx. But instead of writing dy dx, y is equal to x squared. So sometimes you see this, and I do want you to understand that this is really just dy dx because that's the y, right? And I call this the operator form of the derivative. This is like a little thing that's saying like, I want to take the derivative of whatever's inside these parentheses. It's a useful way of writing it, being able to notate what we're doing sometimes. So that's a thing, and then if that's a thing, then you could say to yourself, well, what if I wanted to take the second derivative? That's like taking the derivative of the derivative. So here's the operator form that wants to just take the derivative of whatever's next, whatever comes in here. So what if the thing that you want to take the derivative of is actually just the derivative? So what if you wanted to do that? That's what this is. And then if you see with the way the d's line up and the way the dx's line up, that's the motivation for why we write it like that. And the other motivation is if you put the 2's in the same place, it would really look like you were trying to square something, and we're not trying to square anything. We're just trying to take the derivative twice. So I think that's doubly motivated by not wanting it to look like we're squaring something and this notation. So that's why it gets written like that. All right, so 37, I got an A, B, C, D kind of situation here to find the second derivatives of things. So for A, first derivative, 21x squared minus 10x plus 1. And then the second derivative is 42x minus 10, and that goes away. B, first derivative, I'm not copying down the problems, but I am writing complete mathematical sentences because I care about things that are true and beautiful in this world. Oops, I just read. I just said I'm not writing down the problem, and then I wrote down the problem. That's hilarious. So sorry, that's 24x minus 2, and then the second derivative is just 24. Right? C, dy dx is, oh, okay, so before I do that, maybe I need to do one step. I'm going to sneak it in right here. Y equals, I need to divide through by that x. So that's really 1 plus x to the negative 1. I need to do that because I don't have a rule for quotients like that. I will after the next section. But even if I did have the rule, it's so easy to simplify it to this. This is definitely easier. So the derivative of 1 is 0, and then negative 1x to the negative 2. And then the second derivative is 2 positive x to the negative 3. And then D, again, I need to do a small bit of algebra first and FOIL this thing out. 35x to the 5th minus 21, let's see, 21 plus 5 is minus 16x cubed, right? Those are two x cubed terms when you FOIL that, minus 3x. So dy dx is 5 times 35, let's see, 70, 140, 175 x to the 4th, I think, and then that's 48x squared minus 3, and then my second derivative is 4 times 175, let's see, 2 175s is 350, so it's 700, I think, 700x cubed minus 96x, and then the 3 goes away. So I think that's it. And then 47 and 48. Remember when I accidentally did those two problems? That was funny. So 47. Getting deep into the numbers now. I bet this is real thinky stuff here. Oh, focus on concepts. Here we go. Find a function y equals ax squared plus bx plus c, whose graph has an x-intercept of 1. What does that mean? Okay, pause there for a second. If it has an x-intercept of 1, that means it goes through the point 1, 0. That's what that means. It has a y-intercept of negative 2. Okay, if it has a y-intercept of negative 2, that's the point 0, negative 2. So there's 2 points that are on here. I don't know if you remember this, but like back in Algebra 2, I guess, you might have done some problems that were of the type, here's a quadratic, like a generic one, A, B, C, like this, and then how much information do you need to be able to pin down that quadratic? Well, how many pieces of information do you need to write a straight line? You need 2 pieces of information, 2 points, or a point and slope or something like that. But you need 2 pieces of information because there's an A and a B. If it's just a straight line, like y equals bx plus c, then you need 2 pieces of information because you need to make a system of 2 equations because there are 2 unknowns. And here, since there's an A, a B, and a C, I'm going to need 3 pieces of information because there are 3 unknowns. So I've got 2. If they just gave us a third point, then I could set up that system. But instead, they're telling us that it has a tangent line with a slope of negative 1 at the y-intercept. Okay, so we got to process that. So slope is negative 1 at the y-intercept. How do we write that? That's a sentence, and sentences, if we can capture things in our more concise mathematical notation, that's always a good thing. So the slope is -1 at the y-intercept. Well, what's the slope? Let's see. I can find the derivative of this, right? That's just 2ax plus b. If you didn't get this problem, this is always true for watching these videos. If you didn't get this problem the first time, and now you're like, oh, I think I see where this is going, then pause the video and try to finish the problem yourself. This is not a good time to just kick back and eat some popcorn, or whatever your preferred mathematical snack is. So, if the slope is -1 at the y-intercept, this is the y-intercept. The y-intercept is 0, -2. So this is the same as saying that y prime at 0 is -2. Or in other words, when you plug 0 into the derivative, you need to get -2. Oops, not -2. Where did I get that? Oh, the slope is -1, sorry. You need to get -1. Why do we need to get -1? Because they told us that the slope is -1. They said the slope of the tangent line, that means the same as the slope of the function. So it's -1. Okay, so I need to plug some stuff in now. So this is a point on the actual function, right? This is a point here. So that means if I plug 1 in, so the point 1, 0 gives me this equation. I plug 1 in here, and I need to get 0 for the y. 0 equals a plus b plus c. That's what this piece of information gives me, this equation with a, b, and c in it. All right, this is another piece of information where I plug in 0 for x. 0, that knocks that out, so I just get a c on this side. That's nice. And then this is the y. Now, of course, maybe you knew that the y-intercept of a parabola, just like with a line, it's whatever number's hanging out back here. If you have it in this standard form, then that's it. Okay, so I know what c is now. Now, what do I do with this piece of information? Y prime of 0 is equal to -1. Well, that's just something, the 0, that I can plug into this, right? This is not a number, not from this statement. 0 is not something I should be plugging into this, not for this information. This is information about the derivative. So I plug in 0 into the derivative, and that knocks that out. I just get b equals, and then y prime is -1 there. Right, so it's kind of like plugging in a point, but we're plugging in that information into the derivative because it's information about the slope. All right, so I think that's it, right? I know what c is, I know what b is. If I put the b in the c, -1, -2, a's got to be 3. So y equals 3x squared minus x minus 2 is my quadratic. And that's kind of cool. I mean, sort of a random thing to do, but we just found the equation for a parabola that has a 0 here, 1, 0. It goes through the y-axis here, has this y-intercept, and at that y-intercept it has a slope of -1. Cool, that's it. All right, last one, number 48. Similar kind of thing, I think. You might want to give this a try again if you're feeling inspired. Find k. I've got y equals x squared plus k is tangent to the line y equals 2x. Okay, so I'm going to make a little sketch to try to, this could happen in your mind, I suppose. So y equals 2x. There's that. I don't know why I made a dot there. That was a weird thing to do. There's my line, y equals 2x. And then what does this look like? The parabola, well, y equals x squared, we know what that looks like, and plus k, that just kind of lifts that parabola up or down. So somewhere, looks like it's going to have to be lifted up a little bit here. There's a parabola that's going to graze that just right there. But I don't know where that is. There's some point here that's on this and on this. Well, that's just the intersection of them, and you've known how to find intersections for many math classes, I think. So these two things intersect when they're equal to each other. So I'm going to set them equal to each other and see what happens. So I get x squared plus k is equal to 2x. All right, I still got an x and a k in there, so I don't know how helpful that is. But also, they where they intersect, so let's go here. Let's find the derivatives. Y prime is equal to 2x, and the constant goes away. And then the derivative of this is just 2. I mean, it's a straight line. It has a slope of 2. So that is helpful because wherever they intersect, that's when they also have the same slope there, because this line is tangent there. So I can set those equal to each other, right? Because the problem said we want to find it where this line is tangent to that, which means they, at that x value, they have the same slope. And that looks like that x value is 1, which kind of jives with what my picture looks like. So x equals 1. And if x equals 1, well, I have this equation here, right? So plugging 1 into this, I get 1 plus k equals 2. So k is equal to 1. So it looks like that's all I need to know. What's the value of k? I guess I found it. That wasn't too hard. So kind of similar to tricks that you have done before, I think, finding intersections of things. But we have this new level of what information we can work with. We can think about working with slopes and derivatives now. All right, there you go. Sorry about those extra problems. I probably should say this at the beginning of videos, you only have to watch the stuff that you need from any of these videos. So maybe like a whole bunch of that early stuff you didn't need. But there you go.